Alright, welcome ladies and gentlemen. This is the last video in the series 2E, but many more to come during this year, covering Newton's second and third laws. Now, we have two blocks being pushed across the surface with the external force F as shown in figure to the right. The mass M2, the mass of M2 of block 2, the mass, which is labeled as M2, of the block 2. Okay, this mass is bigger than this mass. Is basically what they're trying to say through all these fancy wordings. I'm sorry for tripping up my words there, but that's basically what it is. The blocks begin at rest and then are getting pushed. So there is acceleration in this case per se, that as we push, we're going to get into to accelerate. So if we have that key note of acceleration, then we can say that the net force in the x, F net in the x, does not equal 0. The F net in the x actually has to be greater than 0. And we want to keep that in mind because we do have this system accelerating. But there's something interesting that we are see that's going to come into play as we do this. So they want us to once again practice drawing the free body diagrams of both blocks relative to each other. And so, of course, we're getting this pattern that we see the two masses are different, and this is something that's going to come up a lot as we draw the free body diagrams. There is no, the blocks aren't floating or sinking. So we know that the F net and the Y, if I want to write that out, the F net in the Y does equal 0. The sum of all forces in the Y does equal 0. So then my normal force here on block 1 is going to equal the mass 1 times gravity. My normal force here, for normal force 2 versus normal force 1, is going to equal this mass 2 times gravity relatively to each other. And of course, this being the greater force of gravity and greater normal force, because of course according to the image in the scenario, this is the greater mass versus the first mass. Now, where is this individual pushing on? Is it pushing on the first block or the second block? This individual is pushing on the second block, and so we're going to represent that with that push, that F of the push, or the force applied. And that's going to be a large force, because our system is accelerating. If you are in doubt about our system accelerating, I do admit for myself that it's confusing from a text. They say it starts at rest, it begins at rest, and then it's changing motion. So of course, if it begins at rest, and then it says it's now being pushed, you know that the velocity has changed. The velocity was 0, is no longer 0. You do have acceleration. That's kind of like hidden in there. But then here at the bottom, it does says derive the magnitude of the acceleration. So I mean, even this keyword here says we are accelerating. And so this is the F push. Of course, that is the only force that this first block, the first one, will feel. This is the second one. Because, I mean, only he feels the push. What's going to happen, though, is that this block is going to feel M2 push back on it. Because M2's sitting here like, no, I don't like to be pushed. What's going on here? And so if we look at it carefully, the fact that, I mean, as he pushes the first block, this second block is going to push back on it. So we're going to say this is a force of 2 on 1. That's the force of the second block on the first block. Sorry, you can't see that there. Let me see, zoom out so we can see everything together. I'm trying here. I'm really trying to get this as the best setting as possible. Please let me know in the comments how far, close, if you can see the words, can't see the words, how can I improve this videos for you guys. Much love to my AP Physics class. Love, heart, tutu. Okay, cheesy, I know, corny. Moving on. So, yeah, even though this individual is pushing this first block, well, this block has inertia. It's going to say like, yo. It's going to slightly push back. Now, it's not going to push back enough to cancel out, but it's going to push enough because to cancel some of it out, but it's not going to cancel all of it out because we have the whole system altogether accelerating. So we need some leftover force positive in the positive x direction for the horizontal axis. Now, what about the second block? This second block is only going to feel one force on it. The second block is going to feel the force of the first block pushing on it. It's really, his second block doesn't see the individual pushing. That's only the first block feels that. The second block doesn't feel the force of the first block pushing on it. And here's where I forgot to mention in the last video for 2D, but you can go back and check for 2D. This is a great application of Newton's third law. Well, if this is the force that 2 feels on 1, well, the force of 1 on 2 is going to be equal and opposite. Oh, there it goes. So we don't have to do much thinking about that. We're going to draw the same vector here. The same magnitude. It might be slightly longer, so let me make this one longer too. I just want to know that these two are equal in magnitude to each other, but opposite in direction according to Newton's third law. And now this is the force of 1 on 2. Bam. Okay, so in scenario, you see that these two forces are equal and opposite of each other. They really represent the two forces at the intersection of these mass 1, the first mass, and the second mass. That one is pushing on the other, and the other one is pushing back on it. But ultimately, both of them are going to move at the rate that that the person who's pushing overall wants it to move at. And so the next part, let me check it real fast. We're going to go through a quick derivation. Let me see where we're at. Check the video in our time. It's needed. Okay, so we're going to see here now. Okay, I'll pull it up again. Push some things back. Is the fact that they want us to derive the acceleration for the second block. Now, what is the actual acceleration on the second block? And so we're going to get to that real quickly. It's very similar to, if we flip back and you can rewatch the video, it's really similar to 2C, where we need to either be able to do the derivation mathematically and explain it, or they're going to give us the explanation and we're going to have to derive the steps as we go through it. So I'll give you a moment to read over the steps. Just like Blue's Clues again. We'll wait while you read. Okay, we're done reading. Let's get back to it. So we know that the net external force, like the overall force, has to be the push, because that's what gives acceleration. So then we can think of this as, we're going to say that my sum of all forces is going to end up being my push, whatever my push is. F push equals my mass times acceleration in the x. So it's taking this, all my forces added up with the forces on the blocks in each other. I mean, ultimately we look at this, these two forces can cancel out. So if these two forces cancel out, then my net force is just the push. That's all it is. Equal and opposite. Blocks push against each other, cancel each other out. And since they cancel each other out on the internal force, and that's really what the last one, the eliminating internal forces, if you notice that some of these forces disappear because these two forces disappear. Kind of like being pushing this way but pulling this way, these two cancel out. Being pulled this way, being pushed this way, pulled this way, whichever frame of reference, these two cancel out. So ultimately you're just left with this force from the first train. That's really what's exerting and carrying through to the others. So we're going to eliminate these two internal forces and just be left over with my net force, F push. Well, if we notice that, then we notice that the mass of this entire system being pushed is really the first mass plus the second mass. M1 plus M2. And so that the acceleration of the system is then, if we rewrite this, AX equals the F push, FP now, divided by M1 plus M2. I'm going to rewrite this over here. AX equals F push. Sorry for my head. I just noticed my head was in the way. Divided by m1 plus m2, I'm just rearranging this top equation here that we started here, then got F push, corrected the mass, accounting for both masses, is what the total mass is, and now rearranging to solve for acceleration, the x, this is what I get. And since both of these blocks will be accelerating at the same, it's not like one is going to be faster than the other, or block 2 is going to be faster than block 1. No, this is an entire system. We consider this an entire system now. And this is really what you should hint at these first 5 videos. What do we consider a system? What part of the system are we analyzing? Are we analyzing the whole system, as we're doing here? Or are we analyzing individual parts of the system, as we did here? You really have to focus on whether I'm analyzing an internal part of the system or the overall system as I do these problems. Well, in this case, since block 2 is really going to accelerate as the whole system, well, I can replace this AX here with an A2 and say that, well, the acceleration of block 2 is going to be the same as the acceleration of block 1, is going to be the same acceleration of the entire system in the X. So I can just say, without a doubt, and since mass 2 will have the same acceleration as the system, the acceleration of mass 2 is just equal to F push divided by m1 plus m2. Cool. I hope you're watching these videos. They are a part of the class, and I know they're supposed to help you study. And so hint, 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 the last video, if you did watch 2D, I left some to do for your own. That I started with check. And so once again, in this last part, since I did the first 3 videos entirely, in these last 2 videos I'm tapering off so you can do more on your own, I'm really looking at you doing this part, because they're adding in a third block. Okay? Will the acceleration of block 2, he's pushing with the same force. Pushing the exact same force as he did in this 2-block system. But now the same force is applied to a 3-block system. Will this block of the M2 have the same acceleration, a smaller acceleration, or a larger acceleration? My hint? Go back over here. What do we do here for the total mass? How will that affect your acceleration? Is it still just M1 and M2? Are you dividing your overall same force of push by a different mass? The same mass, a larger mass, or a greater mass? If you have that thinking mathematically, then you can figure out, well, then what happens to acceleration? Will it stay the same because it has the same mass? Or will the acceleration decrease or increase depending on what you are dividing by, a greater mass or a smaller mass overall? I hope you can follow that. I mean, that's as much hints I can give without actually doing the problem for you. Like I said, I'm going to check. So the 3 parts I'm going to check. This one from 2E and these 2 problems from 2D. Thank you, and I hope you enjoy the rest of this Sunday, the 8th of December AD, after the death of our Lord 2019. Thank you, and have a great, see you guys all tomorrow.